A very good day to you. Today we are in the last section for chapter 3 on the simulation of reactive processes. So for the last part of chapter 3, we have 2 learning outcomes. So let's refer to the slide. So the first outcome is you should be able to simulate the reactive processes using the kinetic in partial pressure basis. And second, you should be able to simulate a multi-tube reactor using the R-plug model in X1+. So referring to the figure below, it is actually a multi-tube reactor, and the tube in red color is actually one of the tube inside the multi-tube reactor. So the content for the lecture today, or for you to achieve the outcome today, is through exercise 3.7. So we have the case of glycerol dehydration. Okay, first to acetol, and then acetol will then be hydrogenated to propanediol. I think this case is similar with the case that is given in exercise 3.2, but in exercise 3.2 we'll be using only R stoid, and here for this example 3.7 we'll be using R plug because it is being carried out in a plug flow reactor. Okay. So as mentioned, there are 2 reactions as represented in equation 1 and 2. We have glycerol dehydrated to acetol. Acetol will then hydrogenated to propanediol. That's why we need hydrogen in the process. So of course our desired product here is 1,2-propanediol. So the rate equation for these 2 gas phase reaction is given in equation 3 and 4. As mentioned, it is in terms of partial pressure basis. P is partial pressure in the unit of kilopascal. K is the rate constant in the unit of kilomole per meter cube per second. And obviously for first reaction, the glycerol dehydrated to acetol, we have first order reaction to glycerol. And for the hydrogenation of acetol, we have second order reaction, first order in acetol and first order in hydrogen. As usual, the K, the rate constant here, can be expressed in terms of Arrhenius equation. And from the Arrhenius equation, we get to know the pre-exponential factor and also the activation energy. Okay. So for the feed, the crude glycerol consists of 78% of glycerol and the balance of water, and it is feeding into the system at the flow rate of 1 kilomole per hour and mixed with 5 kilomole per hour of hydrogen before it is entering to the reactor with the dimension of 5 cm in diameter and 200 cm in length. The feed temperature and pressure are 200 degrees C and 1 bar respectively, and the reactor is operated at the same condition as the feed. Your task now is to simulate the process using an RTL-RChem method and determine first the conversion of the glycerol, second is the number of tubes in a multi-tube reactor if you would like to produce 50,000 tons per operation year of propanediol, and with the number of tubes calculated, you need to verify the answer through the simulation. So there is a note given here. 1 operation years is actually equals to about 7,920 hours. How to get this number? We use 330 days multiplied by 24 hours because we assume 30 days, about a month, is used for maintenance purposes in the plant. Let's analyze the problem. So as usual, we have to list down the component. So component involve glycerol, water, acetol, hydrogen, and also propanediol. And we have the property method given is NRTL-RK, because I think it involves both liquid initially, then we have also vapor phase in the reactor, the vapor phase. For feed information, there are two feed. Feed 1 is a glycerol, 1 kilomole per hour with the composition of 70 weight percent of glycerol, 30 weight percent of water. And feed 2 is actually the hydrogen, pure hydrogen, with the feed flow rate of 5 kilomole per hour. So you have feed 1 and feed 2, meaning before entering the reactor you need a mixer. So the reaction information given here is we have the rate equation in terms of partial pressure. Obviously this is a gas phase reaction, because normally when we have gas phase reaction, the kinetic is expressed in terms of partial pressure. And we have to use R plug here, okay, because kinetic is given and it's a plug flow reactor. The phase in the reactor is we choose vapor liquid because I think initially the glycerol is in liquid phase, but later on it is changed to gas phase in the reactor if it's in the real plant, right? At normal temperature and pressure, the glycerol is actually in liquid phase. So to be safe, we choose vapor liquid for the reactor valid phases, and the reactor operating condition is just the same with the feed. Okay, now let's solve the problem. We have first question, determine the conversion of the glycerol. So as usual, we have to list down the component, then we have to choose the property method. So in the case of if the reaction phase is not given, because in this question it's given, it's saying that the reaction happened in vapor phase. But if it's not given, you can actually check the boiling point of the component in the list of component. Okay? Under the list of component, then you have to click review. So once you click on the review, the properties table will be given to you, and TB here is referring to the boiling point of the component at the atmospheric pressure. Okay, bear this in mind. So this TB, the boiling point stated here, is actually the TB, the boiling point for the component at atmospheric pressure. So if the operating pressure is increased, then the boiling point of the component, of course, will be increased. You can also predict it using Antoine equation. If your operating pressure is higher than the atmospheric pressure. So once you have done that, then from property environment, you shift it to a simulation environment. So here you have to include or construct the flow sheet. As usual, put in the block. We have, as I said, you need a mixer to mix up glycerol, the crude glycerol with hydrogen before the feed is entering to the reactor, R101. You have to choose R plug. Okay, and once you put in the appropriate block, then you have to connect the block with a stream. Okay. So S1 here is referring to the crude glycerol, and S2 is the hydrogen. So next, you have to include I think this is the reactor operating condition. So you just choose that the reactor is operated at constant temperature, 200 degrees C, and no pressure drop, meaning the pressure of your reactor is just the same with the pressure of the feed. Okay. So once this is done, then you shift to configuration, put in the dimension of the reactor. We have length given and also diameter given as 200 and also 5 cm. The valid phase here, I have chosen vapor liquid. So you have to now include the reaction details. Just click new and then the new reaction set will be created, R1, and you have to enter the type. Make sure you choose the type of general. Okay, don't choose any other thing but general. Once this is done, then just click OK. Okay. So if you don't know which step to go, you can actually click the next button here. Then you'll be guided to this reaction 1, okay, reaction folder for you to include the reaction details. As given in the question, there are two reactions. First is glycerol dehydration, second is the acetyl hydrogenation. So just put in the chemical equation accordingly. One mole of glycerol will be producing 1 mole of acetyl and 1 mole of water. And for the second reaction, 1 mole of acetyl will react with 1 mole of hydrogen, and this will produce 1 mole of propanediol, right? So this one, PG here should be PDIO. This is the old file. I have actually copied from the old file. The new file is revised with PDIO. Okay. Can you see this one? Okay. Now, with the chemical equations given in the configuration tab just now, just click next. You will be guided to kinetic section. There is a drop-down list. You have two reactions in the list. First one is the glycerol dehydration. Just choose vapor phase, and then the basis of the rate equation is partial pressure, remember, and the unit for your pressure is kilopascal. Make sure you have chosen the correct one, and the unit for rate is kilomole per meter cube per second. You can just leave this. And we have a K value given in the Arrhenius equation, the pre-exponential factor here, and also the activation energy given in the question in terms of Arrhenius equation. And once you have done this for reaction 1, you have to put the driving force, the order of reaction. It is first order in glycerol. Okay. Once this is done, just close and include the kinetic for the second reaction, the acetyl hydrogenation. Just put in accordance to the kinetic given in the question, and remember to put the order of reaction through the driving force section here. Remember to do this. And just to remind you, this is a very common mistake among the students. Students always forget to include the driving force, and this will result a wrong simulation output. So once this is done, remember our task is to calculate the conversion after the simulation. What you need to do is run the simulation, get the result under stream result. This is the stream result. Again, you have to check the glycerol conversion. Okay? Conversion is always referring to the reactant conversion. So we have S3 and S4. This is inlet and this is outlet. S4 is the outlet stream. So glycerol here, we have the inlet stream for glycerol and outlet stream for glycerol. Just put into the equation for conversion, and the resulted conversion is about 63.3%. So this is the answer for question A. So let's move to question B. You have to determine the number of tubes in a multi-tube reactor if you would like to produce 50,000 tons of propanediol in one operation year. Before you do anything, you have to change the number of hours in one operation years to 7,920. So just go to setup under the simulation environment, setup. So here there is a term called operational year. So just edit the number of hours here to 7920 hour. Once this is done, then you have to go and check. I think before that you have to run the simulation again using the file just now. Okay, reset and run the simulation again. Then let's check the propanediol in one tube. Okay, and the unit, the mass flow unit is tons per operation year. So it is 115.467 tons per operation year if you use one tube. Now you need 50,000 tons in one operation year. So you have to use 50,000 divided by 115.467. You get 433 point something. But we have to always round up because number of tubes must be round number. So we round up to 434 tubes. So with this, we have to proceed to verify using the simulation. So meaning the answer is the number of tubes required to produce 50,000 tons of propanediol in one operation year is 434. So put this into the simulation and verify whether you can get this 50,000 tons per operation year. Now, if you want to produce more, of course you have to feed in more, right? So make sure your feed flow rate now is 434 times higher than the original one. So for glycerol, instead of 1, now you have to use 434 kilomole per hour. And for hydrogen, instead of 5, now you have to use 2,170 kilomole per hour. It must be 434 times higher than the original. And now, in the reactor configuration, you have to check the multi-tube reactor and then include the number of tubes here, 434. Okay, the rest is the same. So with this, I think all the required info is completed. Just run the simulation and check the result. So under the stream results, again under the block of reactor R101, check the result. In terms of tons per operation year, you are getting more than 50,000. Okay, it's about 50,123 tons per operation year. Now we verified that we are getting at least 50,000 tons per operation year of propanediol using a multi-tube reactor with 434 tubes. Okay, so this is the answer for question B. So with this, I would like to thank again for your attention. I hope you can at least bring two outcomes back home. One is you should be able to simulate the reaction with the kinetic in terms of partial pressure basis. Okay. Second is you should be able to simulate a reaction in a multi-tube reactor. So with this, thanks again, and I wish you all the best in your quiz.